All right, let's take a look here at our last example with number 4. We'll see again, this is very analogous to stuff that we did back in the last section. Consider the iterated integral. It's already set up here. I don't know what the function is, but I can already see the bounds on the z's, the x's, the y's, and I want to attempt to re-express this integral with differentials in a different order. Okay, now remember that sometimes reorganizing stuff like this can be helpful because sometimes integrating in one order is a bit too difficult and integrating in other orders can make things simpler. So I'm going to start here by thinking about what we already know about the solid and what we already know about the region D that we're working with. Okay, so here's where I'm going to start. We see that the region of integration, that is the solid that we're integrating over, is, well, that's our E, and that's a bunch of x, y, z coordinates. And I can see the bounds. Z is automatically wedged between 0 and y. Y is, or sorry, x, excuse me, is wedged between y and 1, and y itself is wedged between 0 and 1. So this is the information I'm starting with. So I kind of already have a description of the solid. I just don't really know what the solid looks like. Okay, but I'm also then able to kind of tell from this that if I kind of zeroed in, I could probably figure out what the region D is. That kind of works with that inner double integral. So maybe I can go ahead and work with that really quickly. I'll say also the projection into the xy plane is D, which is a bunch of x comma y points. And again, the bounds here are going to be the same. I just am excluding that bound on the z. But from this, I might be able to at least draw what this picture looks like. Here's a picture of D. I know that my y values go from 0 up to 1. And I know that my x values go from a function y, so that's like the function y equals x, and they go over to 1. So the small side, the left side is the function, and then I hit the value of 1. So I would think that this region right here is the region D. I think I could double check, right? My y's go from 0 to 1, and my x's go from y equals x out until they hit 1. Seems like everything fits. But with this then, hopefully I can get a picture of the actual solid. This is kind of tough to do, but we can try to go ahead and experiment with this. All right, here's what I'm going to try. Let's suppose that's my x-axis, and here's my y-axis. My z-axis is going to pop up here. I can kind of start to draw my little triangle. Here's like y equals x coming out. And there's my region D, right? I'm going to kind of sketch it out again in blue. There's my region D. That's on the base. So this is kind of like the floor of my solid. And what I can start to tell is that the bounds on Z are going to help me understand how the ceiling of this works. Notice the lowest that Z can go is 0, but the highest it can go is Y. So you'll notice then that the closer I am to the x-axis, right, the smaller Y is, the smaller the ceiling gets. But as I continue to step into this region, kind of moving down the y-axis, my ceiling should get higher. Now, if y automatically goes all the way up to 1, then the highest that z could ever be is a 1. So let's just say, for the sake of argument, boom, this is how high this particular thing gets. And I can tell that as I walk backwards towards the value of y being 0, I'm going to decrease. And as I walk back, I decrease. And I can create a 3D solid that looks like this. Notice it has that blue base, but these kind of black edges. It's very similar to a shape that we already constructed. It's kind of like that pyramid sort of a shape. I can see all the different back walls. Now that's not super easy to construct, and it takes some time to get used to. But once I have that, it's pretty easy to start taking a look at how I could possibly reverse the order of integration. Because if I want to reverse it to be with y's, I need to kind of figure out what's the smallest that y can ever be and what's the biggest that y can ever be. Now there's a couple different ways I could attempt to determine this, but I do want to realize that I'm trying to restrict y first. Okay, so here's what we got. Hopefully we would agree with the following. Since we know some of the bounds here on y, we might be able to make some adjustments or make some statements. So I'm going to look at the inequalities that involve y. So we know this, and we know this. These are inequalities that involve y that don't automatically tell me that y goes from 0 to 1. While that's a true statement, I want to make sure that I understand that y can be bounded between two functions. It is the innermost integral that I'm going to set up, so I want functions. Using these two, I can start to see that y could also be wedged between two functions. Notice that y is always smaller than z, but it is always bigger than x. Once I have this, I could start to go ahead and identify, hey, this is bounds on x, and now, or sorry, bounds on y, and now I could think again about the projection into the remaining plane. So I'll say we then project E into the xz plane. So take a look at the picture up above. Again, I'm trying to imagine the shadow that's going to get cast in the background of this xz plane over here. And you might be able to kind of tell that I'm going to get something back there as a shadow that maybe looks something kind of like that. Right? You can kind of see me drawing it in the picture. I have to kind of really practice, like what happens when I view the solid from this direction. So if I was to try to draw this, oops, in the xz plane, I could see that I'm going to have, let's see, the furthest out x goes is 1. We were told that before. That was a bound on x. And the highest up that z went before, we saw was y, but y went all the way up to 1. We said that highest was 1. So then if I kind of connect the dots here, and I can kind of see how some of this works, I can see that I kind of get out to a point in the xy plane of 1, 1. Right? That's kind of what this point up here, it's 1, 1 for x's and z's. Or I'll write it, I guess, out here in the coordinates 1, 0, 1, since I'm in the 3D picture. But I kind of have then this line that goes back towards the origin and kind of comes up from x equals 1. This is like that red region that I have. This is my new D. For the moment, I'll call this region A. I'll then be able to define A using double integral techniques. Since I want to set it up as a dz dx, I'm going to bound z first. Can you see if you could try to set up what this region would look like if you bounded it? Bounded z first with functions and then x with numbers. Take a moment to see if you can pause the video, try it out on your own, and then we'll come back and you can watch my result here. Okay, so the result that I'm getting would be that the line that I have here is just z is equal to x, and so I can see that z is bounded between 0 and x is bounded between 0 and 1. So I could say that my triple integral, when I reverse the order of integration, well, let me word it like this. I'll just say the answer is, and I'll have my triple integral, and I can rewrite the bounds. My x bounds come last, my z bounds are coming second, and those bounds on y, oops, are coming first. So y, z, and x. And there we go. Again, the hardest part of this section is visualizing these 3D solids. Don't get too bent out of shape if you struggle with that. That is the most common thing that people would struggle with here. It's very difficult, and it's not, again, something that you've practiced a ton in other classes. It's not like this is an old algebra technique that you have to refresh on. So if you're a little slow at it, you don't feel entirely, almost well coordinated at working with it, that's okay. Give yourself some time. Just don't give up and stop practicing as a result. Okay? This kind of wraps up everything that we need to know about triple integrals when working with rectangular coordinates. In the next sections, we'll start to look at what happens if we introduce other coordinate systems.